Thank you very much for joining us, guys. We've got a very exciting case to share with you today, which is going to be really concentrating on how we are not only solving data science problems, but actually applying them to the business. So we already had an introduction, but I'm Nikita Medvedev, Director of Advanced Analytics, and my co-presenter.
Yep, Winston here. I'm the founder of Arima. All right, perfect. So I'll kick us off with a quick introduction of the Synthetic Society, which is what we do at Arima. The Synthetic Society is a modeled version of the Canadian Society. It contains 38 million individuals, each of which is attached to a postal code, and it contains more than 5,000 attributes. So let me take a little bit of time to explain what that means. The reason why it's called synthetic is because of the fact that we leverage synthetic data generation technology. And for most of you who are familiar with data science, synthetic data has been a really popular thing in the last couple of years. The reason why we leverage synthetic data is obviously because of privacy reasons. So there's lots of different privacy regulatory reasons where we're not able to use the original data set, and therefore people have came up with this clever way of generating a synthetic copy of the original data set. A synthetic copy of the original data set is generally not exactly the same as the original data set, but it contains similar statistical features and similar data science properties so that you can apply models, you can train models and apply that to real data set. So think of it as creating a digital twin of the original data set. And that's exactly what we're doing here. We work with lots of different data sources. They're all consumer-centric. So they include things like the census, market research, mobility data, things that we'll be talking about today. And we create synthetic copies of them, and we map them to the entire population. So hence, in our database, you have 38 million individuals exactly built to match the Canadian society. These individuals are not identifiable by name or by any personally identifiable information. So the purpose of using the Synthetic Society is not for you to trace back to individuals, but rather to build better models. Here we go. I want to quickly talk a little bit about what's in the Synthetic Society before pass it off to Nikita. The Synthetic Society contains behavioral data, so common things like demographics, psychographics, purchase intents, healthcare, media consumption. Depending on the industry you're in, you may find some of that useful, but they're all, of course, geared towards consumers. So this is a consumer data set. Data is available at the individual level as well as the postal code level. So depending on your application, you might find one or the other being useful. If you're trying to match that to your CRM database, for example, you want the individual level data set. But if you want to map it to a geography, so for example, looking at the surrounding area of your stores or things like that, you may be fine working with the postal code level data. And finally, the data set is, of course, quarterly updated. What's probably more interesting, and also the reason why most of you are here, I assume, is because of mobility data, which is the other thing that we capture through our Synthetic Society data sets. It's a daily feed of movement patterns. So for every individual, we capture a hashed device ID. We also capture lat and long, a timestamp, as well as your speed of travel. And with that, based on that information, obviously, we can infer a lot of useful information, like whether you visited certain places, your shopping habits, whether you work from home or in the office, and so on. This particular data set is pinged about every 5 to 10 minutes. So we capture about 125 data points per day per device. Of course, everybody comes with a postal code as well, and that's how we integrate with all the other data sources. So that's it. That's a quick introduction of the Synthetic Society. Now I'll pass it over to Nikita to continue the conversation.
Thanks, Winston. I am from Coca-Cola Canada Bottling Limited. So let me spend a couple of minutes just talking about what is it exactly that we do, how do we operate. So Coke Canada is operating coast to coast. So we've got 5 manufacturing facilities, 50 distribution centers and warehouses, as well as more than 6,000 people working within our company together with us, all to serve our 38 million consumers. As you can imagine, with this amount of bread, there's quite a few challenges. Now, what exactly is it that we create, that we produce? You might be aware of Coca-Cola itself, of course. I'm from Coke, hence we sell Coke. But not everyone is aware that we have more than 25 various brands that you can see here at the top. We're in multiple categories: energy with Monster as an example, Dasani Smart Water, Vitamin Water, Fanta Sprites, Nasty, even in dairy with Fairlife and Core Power. Very exciting portfolio, and that number is actually kind of low. It's not 50 packages, more than 100, far more than 100. There you go. So what is it exactly that we do? Coca-Cola Canada Bottling Limited is the Canadian bottler for Coca-Cola. What we do is we make, distribute, merchandise, and sell all of the Coca-Cola products within Canada. If you ever picked up one of the Coke brands in any of the stores or any of the vending machines anywhere, you probably dealt with one of our products. Where do we operate? We operate in multiple channels, supermarkets like Sobeys and Metro, hypermarkets like Walmart, club stores like Costco, convenience, drug, wholesale, and so on. Today, we're going to be concentrating on what we call our FSOP channel. FSOP stands for food service and on-premise, and that is encompassing our large restaurant chains, for example, like McDonald's, and all the way to the mom-and-pop restaurants that you might have down the street from you. One important part of this is our vending business, what we're going to be concentrating on today. So, vending business. I'm sure most of you have seen our vending machines. Nice, beautiful vending machines right on top. What you might not realize is there's 26,000 of them across Canada, serving a variety of various brands. Here I have a small heat map of where these vending machines are located. And you might immediately pick up that all of those red and green dots, they're around big population centers, which makes sense. You don't want a vending machine in the middle of nowhere when there's no people around. We're trying to serve our customers in the best way possible, and that means being in the right locations with the right products at the right time. Hence this project, making sure that we are concentrating on who exactly is traveling close to our vending machines. So what problem are we actually trying to solve? What we're trying to figure out is how can we improve our customer service through identifying ideal locations for placing our vending machines. Location is really the key. So what really matters for solving this problem? What drives the vending machine business? Of course, being a beverage company, seasonality and weather is extremely important to us, which I believe makes a lot of sense for everyone. Another important factor is the assortments that we have within our vending machines. This applies to most of our business, but specifically vending machines. With assortment, what I mean is what products do we have available there? Are they serving the purpose? Are they providing the specific products that people would want in that location? And what we're going to be talking about today is that middle area right there, which is the location, demographics, and footfall. We want to be in the right places. We want to be in the places where people are. We want to be in the places where people need us. So what data are we using to solve this problem? Of course, we're using our internal data, which we're just calling vending machine data here, as well as demographics and mobility data that Winston has just walked us through. So with our internal information, of course, what we are really looking to measure results and what we're looking to predict is the sales of the vending machines. Now, the sales for the vending machines we're using as a proxy to measure our business, to understand, are we serving our customers better? Are we making sure that everyone in this line, in this value line, is benefiting? We're looking at the location, we're looking at a lot of other factors, but I wanted to highlight two main things, two main features that we extracted from here that really mattered. We're talking a lot about location, kind of the geospatial location, but what also matters is not just where the vending machine is, but what is specifically around it. And here we're looking at the specific channels. As you can imagine, a vending machine placed in the transportation channel, which for us would be something like the Union Station, is quite a bit different from a vending machine that might be in a hotel lobby. And exactly the same idea applies to the various regions that we're looking at, as our business in Ontario would be very different from Quebec. Demographics. So with the demographics, oh my God, it was a lot of features. But here we have, just highlights the groups for some of them. We're looking at age, self-reported gender, marital status, profession, personal income, education, all the good stuff. And we'll talk more about this later, how we're dealing with the curse of dimensionality. Last but not the least, and I'm a big fan of this GIF, is mobility data. Mobility data is, as Winston was mentioning, is data on traffic patterns of the people around our vending machines, around our business. They allow us to understand who is traveling close to the locations that we're scouting, and helps us understand who these people are and how we can improve our business to serve them better. So what kind of features were we trying to build out of this? One of the first ones that we were dealing with was trying to understand the patterns of the movements of traffic patterns throughout the day. At the top end, it's very tiny access, you can't really read this, but that graph that you're looking at is a 24-hour graph of what the traffic patterns look like in any location. We just picked a typical one. And that each bar is a minute. As you can imagine, it's a lot of data, it's a lot of complexity. We had to simplify it somehow. In order to do this, we also did not want to really get too far away from our real people and wanted to connect this to their journey, to the consumer journey. So here we tried to understand why are people moving around at this time? Why are customers moving around at this time? And the groups we come up with are groups like our rush hour travelers. This would be people commuting to and from work. So here we're capturing traffic in between 6 a.m. and 9 a.m., 5 p.m. and 8 p.m., for example. And because, as you can imagine, this would be quite a bit different from the late night travelers, people who would be at social events or traveling back home from them. Different times, different purposes, different reasons, and different beverages we should be providing them. Same exact idea we applied to patterns throughout the week, of course, where we saw three main groups. We've got equally split traffic throughout the days of the week, as well as certain locations were much, much heavier during the weekdays, and certain locations were much, much heavier during the weekends. So with all of this, we try to make sure that we're capturing this in our specific features that we're building out of this. There you go. So our modeling journey, and I'll go into more details about this. Initially, we started with trying to predict the sales for this as really the target variable. Naturally, with sales, you're looking at a continuous variable. Therefore, the immediate reaction is, let's slap a linear regression on this, see what happens. And of course, we got pretty bad results. Enormous overfitting, too many variables for a linear regression, very low accuracy, it was below 20, it was unusable. But it's always great to get that baseline to understand what you're starting with. So then we started looking at how can we fix this, what are the real problems here? And what we saw is two main issues. Number one, it was the curse of dimensionality. We're dealing with more than 128 variables here, and 128 features. And on top of this, our target variable was not really fine-tuned to what we're really trying to predict, what we're really trying to do. And this allowed us to evolve into our next steps. First, to move on to regression-based classification, which really helped us boost our accuracy. And after that, the real discovery here was reworking the whole problem into a full-on classification problem. So let's go through this one by one. So the first step is the curse of dimensionality. While we use some just purely logical techniques of being able to group some of these features, some of these features into logical groups to be able to collapse some of those dimensions, we also utilized the dimensionality reduction techniques. I'm sure most of you guys are familiar with principal component analysis, which we utilize quite heavily here. It was super useful, especially on the demographics data. Next, the real important business decision that we've had and real breakthrough in our modeling journey has been reworking our target variable. It's very natural to get stuck with the idea that when you're dealing with anything like sales, a continuous variable, you must do some sort of a regression. But in searching through a lot of the literature on these topics, we kept running through many cases where actually reworking this problem into a classification problem gave us much, much better results. Specifically, investment machine learning industry is utilizing this technique a lot. What that means is getting closer to the actual decision that we're trying to do. What we were initially imagining was we predict the sales for all the locations in order to be able to understand which locations are better or worse, and use a certain thresholds to classify all of them afterwards into pick or no pick locations, basically the locations that we want to place vending machine in or not. But instead, what really helped us is skip all of those steps. jump straight to that prediction of whether this is a good or a bad location. In order to do this, we went back to our training data. We relabeled all of this based on certain thresholds for the sales into whether this is a great location for us or not as great. And after that, we were able to train the models on this. And I'll go into the results of what we got from this in a second. The next part I want to talk about before I jump into some of these results and outcomes is what did we use to measure the actual business impact. And here we use the concept of expected value, which I'm sure all of you are familiar with as well. But if you're not, it's simply the idea of when you have multiple outcomes, all of them that have uncertain probabilities attached to them, you're able to still simplify this into one metric that basically answers if you were to repeat this experiment over long periods of time, basically infinitely, what would your results actually average out to be, which is simply a weighted sum by the outcomes and the probabilities of each and every single one of these. Okay, so as I was mentioning, we went through multiple steps. After the initial linear regressions, we went into using the regression-based classification. Here you can see our pipeline, how it's flowing. Main highlight here, I would say, is that we end up with using XGBoost for this experiment, which is working very nicely. And when we were doing this, we were trying to really come up with a good way of measuring the results. So the initial one that is very natural is to take a look at the confusion matrix, take a look at the probabilities, and the percent of times our models are predicting things correctly. So the first table I have over there is our default. Essentially, without this model, 45% of the time, the locations that we picked normally were above our threshold, where we consider this a great location, and 55 were below. Now, keep in mind, it doesn't mean that 55 are bad. It just means that they're not as good as we would have preferred. After we utilized this specific approach with the model, we ended up with these probabilities. And this is not, I know it's, this confusion matrix is confusing. Because it's not a confusion matrix by itself. Here we're looking at the probabilities, the splits between the accuracy for the specific predictions for the model. The conditional probabilities, essentially. What this is telling us is when the model is suggesting that this is a good location, 48% of the time it is actually corrected at 52 it is not. That is a 3% improvement from our default, which is really, really not a good result. It's really tiny and hard to work with. But the important part here is that this does not stop here. It's not just about the probability of the prediction being correct. It's also about the expected value that we're getting out of it. So kind of extending this idea, we try to understand how much is this actually impacting our expected value. For all of this, to measure the results, we're using the average expected value that we have without the model whatsoever, essentially in our default scenario. You can see that number as the green one, where here we just indexed all the numbers to help the understanding. And what we see is when our models are predicting the locations correctly, the expected value of that vending machine jumps up by 98%, almost double. But when it's wrong, it is only giving us 42% of the average that we had before. All of that combined, if you take a look at the combine all the conditional probabilities, you can see that we're getting a 17% boost by utilizing this model. Essentially, by using this model, by listening to the predictions of it, by the recommendations, we're able to get 17% better results. Definitely better, but still not good. So we continued our exploration of different approaches. And the next one was reworking our target variable into the direct prediction of whether this is a good or not a good location, turning this into a classification problem. And here we're using the XGBoost, but here just for the classification in this case. And with this, the results we were able to get were significantly better. It gave us a very good boost in that accuracy. If you remember, previously we're dealing with 48%. 48% of the time the model was picking the correct locations. And now we are looking at 68% of the time when the model is predicting that we should use this location, and it actually turned out to be good. Very good boost, 23%, but it doesn't stop here. What we also saw is that once we take a look at the expected value of all these outcomes, we got a bit of a boost for the correct ones when the model is suggesting we'll pick this location, and it was correct. We'll have a 102% improvement, so a bit more than double, which is still kind of similar from what we had in the regression-based approach. What's really cool here is that this is also improving the bad guesses. So when the model is recommending a certain location, but it got it wrong, we're getting 79% of the average results that we get without the model, which is a big boost from the 42 that we saw previously. All of this combined is giving us an expected value of utilizing this model following its recommendation of an additional 43% to our revenue, which is extremely important given that this is our measure of really, are we improving the business? Are we helping our customers? Or making sure that everyone in this chain is benefiting? So, the next, of course, this is Toronto Machine Learning Summit. I had to have a architecture diagram. It's pretty straightforward. We're in Azure shop. Therefore, right in the center, you see Databricks, which is really the big workhorse here. Now, let's talk a little bit about the business implementation of this. So right now, we have been going through market testing, which is giving us good results. And we're looking to continue our experimentation even further, meanwhile scaling up the solution to all of our business. Now, how does this actually fit into the whole flow? How does this fit into going from an abstract data science problem into an actual business solution? So the process for us really is to start with scouting the locations, taking a look at what are the possible locations for us to pick to begin with. From this is going into the model, which then we have a choice. And here we adapt to the reality of the business. All of our regions, all of the different situations have a different approach. Specifically, what I'm talking about is, in some cases, in some areas, regions, or times, we might be dealing with a lot of locations, but not that many actual vending machines that we want to place in them. So because of this, we want to be more picky. With our models, we can pick the thresholds of confidence that it would need to classify something as a good location. The higher up the threshold is, the higher the expected value is, but at the same time, the number of locations picked is significantly decreasing. In the case of us not having that many vending machines to place, this is actually a good idea to increase the expected value, and I will essentially have this approach. But in some cases, we might have the opposite. We might have not that many locations, a lot of vending machines. We can lower the thresholds, have it pick more, but with less expected value. But as a total, we still end up coming up ahead. And from this is getting fed into actual model, gets scored, and comes out as recommendations for the business of what to do next. Awesome. So one last thing, guys. I had to do a small pitch. If you find this interesting, our team is actively expanding and hiring. We're looking for an MLOps engineer, data science manager, data scientist, and senior business analyst as well. If you're interested, please go to our career website, which is right here. Awesome. Well, thank you very much, guys. Are there any questions? Meanwhile, I can drink a Coca-Cola product on camera.
A question, first of all, just a clarification. Is the decision here is about the location of the machines? In this project, you're actually going to move machines around based on the decision that the algorithm picks best location for a vending machine?
Yes. So not necessarily move around. Our goal really is looking at the new locations, new vending machines. There is potential to move machines around as well.
So the second question is about optimizing the mix of products within each vending machines, right? Because you have a whole range of products. Are you attempting to tweak the mix of products within each machine based on the traffic around the vending machine?
Oh, we absolutely are. It's a whole different, presentation in of itself. Definitely a complicated issue. Yes, we are actively dealing with this. We want to make sure that the products we have are fitting what people need. Everyone has a different purpose. As we were saying with our commuters versus somebody going to the gym, they would want a very different selection. So yes, absolutely.
So my question is, have you treated those locations independently, or the sales in one location can affect the sales in another location, so that can affect your overall decision?
Would you mind repeating that? It's a bit hard to hear with the...
So did you treat those locations independently, or you consider the possibility that the sales in one location can affect the sales in another location next to it?
So in this case, yes and no. So absolutely, but here we're not picking locations that are too close together. This was simply because we're at the initial stages of implementing this, where we did not really get to that level of saturation just yet. It hasn't popped up as a massive problem. As you can imagine, the introduction of our products is definitely a big problem if you look at a large store channel. You go to Loblaw, you see this massive aisle of products, and it's similar people purchasing them. With vending machines, just because of the location separation, them being further apart, it's a bit less of an issue. But absolutely, it's part of the consideration and part of the future evolution. Yeah.
Hi, so I have 3 different questions. The first one, I see that you use transformer. What kind of explanation methods you have used to understand, basically interpret the model for recommending locations? The second question is, have you considered other models when you building the location recommender? I know that there's quite a few.
I'm sorry, if you don't mind, one question at a time.
Okay.
Would you mind repeating the first one? There's a bit of a feedback. It's hard for me to hear the questions.
Yeah. So, what's the explanation methods that you have used, or either the tools as well, for explaining the transformer model that you adopted in the model training?
Well, it really depends on what model we're looking at, because when you're dealing with linear model, it's not really a problem whatsoever, obviously. Look at the coefficient and you kind of can see what's going on. Honestly, standard tools. There's nothing too exciting here. A LIM, CHAP, like that's what we're talking about in understanding the feature importance. One of the most important parts for us was really to move this out of the theoretical data science application and be able to connect this to the business properly, be able to understand the people as much as possible. So in the feature design specifically, what we're really trying to do is connect this with the user story. No, not user story, in this customer story. Make sure that we are not treating people as numbers, but actual people. That's kind of a very important part. And this is where really business participation comes very heavily in.
I see. Thank you. My second question is, aside from the expected value, is there any other metrics that you have used to evaluate the models compared to other options that you have considered?
Oh, well, we're using everything that you can imagine as far as accuracy goes. Absolutely. We went through all the standards checks and balances that were going into very rigorous approach, which truth is I shouldn't be speaking about this. The team is right there. Iki specifically was working on this very heavily. It's more, there's a gap between bridging a theoretical accuracy to the real business application. And that's where the concept of expected value has really helped us. Also, models, a lot of times when you're looking at the accuracy by itself, they're not looking at the outcomes necessarily, especially when your outcomes are not uniform, where it's not an actual yes or no, but there's a different scale to them. And that's where putting the expected value on it has really helped us.
Thank you.
Hi, yeah, I just wanted to ask about, the training data versus the actual application. There might be some data skew in that. In the training data, you already have a vending machine at that location, whereas you're trying to predict where a good next location would be in when you're actually applying the model, if I'm understanding correctly. So my question is just about how, was there a data skew in, say, the data you have available on the locations you've already chosen, and just how did you handle the difference in the actual application versus the training data set?
Hopefully I answered the correct question. A bit of feedback, so I'm hearing like every third word. But with the training and testing data, you're absolutely right. It would have been a big problem if we're just using things as is. The way we approach this is we're treating this as a time series problem, essentially. Where, because the sales data especially was our internal, we've got quite a bit of it, we're able to go backwards and take a look at when the existing vending machines were actually placed into those locations and go all the way back so that our testing data set were the more recent vending machines. And the training one was the vending machines from all the way back to before they were placed. And with this, we're also able to only limit the data to what we would have known at that time. And through this, we're able to test on this data and predict as far as the model is concerned, the future, and making sure that there's no leakage of that future data into it as much as possible. But the real test is the real world test, which was the really important component. With everything we're doing, we're trying to move to that real world testing as fast as possible, do it on a small scale just to see, does this actually work? Because you can use any technique on your data that you want to control for this. Real world application is the only way you'll know for sure.
Okay, thanks very much.
Hi, can you hear me well? Can you hear me?
Yes.
Okay, yeah. So I have two questions. So the first one is, I wanted to understand how you deal with degrading model performance. So let's assume that right now the model is, I don't know, 70% accurate, but due to changes in data or distribution changes, the performance may vary. So you might have to relocate the installed vending machines. So is there any guardrails in place for that? And do you wait before moving the vending machine?
So would you mind repeating that?
So I wanted to understand, like, if the model performance changes, it's not reflecting the actual world scenario. So for example,
So just like model drift is what you're asking?
yeah, so model drift, or it could be other reasons as well for the changes in performance of the model. So yeah.
There's multiple reasons. I mean, first of all, model drift, the market is constantly moving. We just went through several years of COVID, right? And that would have been very difficult to predict. Everything has changed. And now it's changing again, and it's going to continue evolving and changing. The important part for us is to continuously monitor the model actual performance. So not only in our testing, constantly retest on the data that we have available, but also real-world application. As soon as we're seeing that the performance of the recommendations in the real world is not performing, that is a hard cutoff of we need to rework this. But we're also will be implementing soft checks of just simply testing the model on the new data coming in, being able to monitor the performance of the locations we're already placed, and simply retraining at regular periods to ensure that we're always capturing new data.
Thank you.
Thank you. This is a question for you both. Okay. First question here is that what element of the synthetic data was the most discriminating as you actually start developing the models? It seems to me when you look at pick or no pick, it was about sales. So I am presumptuous that it was the purchase intent in the synthetic data that is actually much more discriminating. But I wanted to understand from your point of view, what in the synthetic data was the most helpful in building those models? That's the first question. The second question is very simple. Other than vending machines, for example, has property developers looking for locations, are there any other applications beyond vending machines that you see fusing synthetic data as well as location selection? Two questions.
Do you want to take the first one?
Go for the second one, and I'll...
Sounds good.
Yeah, so the first question, if I heard you correctly, you're asking so the synthetic data, because it has no names or anything, how does that get attached to his first-party data? Is that the question?
So what behavioral data or what data is the most important part as they develop the model?
Oh, what important? That's a question for you. What's the most important part of the synthetic data?
Well, it really depends on what we're looking at, just in general for these models specifically. I can't get into too many details, unfortunately, because it's still, models internal and so on the very nitty-gritty specifics. But whenever you're looking at this, you're looking at quite a bit of demographics information. So you would expect quite a few of those being very important. What I would say one of the most important parts was understanding the patterns of movements throughout the week and throughout the day. That has really been instrumental for us to understand the reason why people are at those locations. And that was probably one of the biggest things that has really popped up. In addition to this, what is surrounding that area? As I was mentioning, it's not just the location specific, not just geographical coordinates, but what channel are we dealing with? Union Station, you can imagine, is quite busy, for example, versus a identical vending machine being placed in a hotel lobby. So I would say those would be the main ones. And you were also asking about potential application. Absolutely, but truth is, no, we were not looking at real estate applications for this. But a similar approach can be extremely useful for similar problems that are based on the location, specifically people exactly there, and not just living around. Yeah.
In the interest of time, we'll have to stop here. But
Yeah.
I will be around after. So if any of you have any questions,
We'll just be outside.
Yeah, you can find us outside. Thank you.
Thank you.